Hello everybody, this video is going to be the last in our series of mixed model discussions, and we're going to wrap it up with a discussion about repeated measures. Basically, when you have a subject or an individual and you're kind of measuring that unit over time or, just repeatedly, it gives rise to kind of some special considerations that we have to look at a little bit more closely to be able to, correctly capture that variation through a mixed model. And essentially what we're going to be doing here, we're going to kind of quickly just go through some of the underlying theory of what's going on. We can't really get too deep into it, but there's just a couple other little intricacies we have to keep in mind when we start modeling these data. And then after that, we're just going to kind of launch into a few examples. So the idea is that oftentimes you'll find yourself measuring the same thing many times, like one after another. And so beyond kind of what we talked about before, where we sort of would say the random effects that we use kind of they're grouping factors, the fact that these groups now represent the same individuals, the same units, this is going to induce some extra correlation in our data. Specifically, we might be able to find that there are certain covariates that vary differently in their relationship with the response between these different units. Previously we would have our random effect and it would just serve to kind of capture some extra variation in the response, but the covariates were not really a part of that conversation, but they can be here. Sometimes these studies are called panel studies, and I'm going to have an example of a data set that's a panel data set. But folks will also call it a longitudinal study as well. But the point overall is that we're collecting data over time on the same units of measure, and we want to see if the trends exist. And then as we usually do, we're going to be trying to link covariates to the response, seeing if there's relationships there, and then possibly, as I mentioned a moment ago, the relationships between covariate and response may change depending on which unit we're considering. So that second aspect there is a little bit more than what we had access to before when we were just doing random effects. All that really did was kind of shift the mean up and down depending on what level of the groups we were talking about. And what I mean by that is previously what we talked about was that whenever we had a random effect, we assumed independence within the groups. Meaning if you knew which level of the random effect you were considering, then the observations within that level were independent of one another. And the way we wrote that out, we had our response, the distribution of the response, given which level of the random effect you're considering. That distribution has a normal distribution with some mean, and then our variance was just sigma squared I. And this I here was just a kind of matrix of ones and zeros like that. And basically each of these rows and columns represented an observation. And just having the ones on the diagonal here just meant that every observation was independent of every other observation. But again, remember, this is given that we know which random effect we're considering. Because we know that random effect, the different levels may shift Y up or down, essentially making it kind of above or below this average. But within the groups, they're independent. But now, with these models we're going to consider in this section, we're going to consider the possibility that we have correlation within the groups also. So the only thing that's changed now when we're considering the situation here, where we want to measure the same units over time, you can imagine, if I'm a unit and I'm measuring, I don't know, how much I weigh over time, I'm taking a measurement every single day, you would imagine that my observations are going to be correlated with one another. And so if I'm the group, you can no longer assume that my observations are independent within that group. There's obviously correlation there. So what we do to capture this is now we have the same thing here, the distribution of Y, given we know which level of the random effect we're considering, has the same mean as before, except now the variance has this capital lambda here, which will be something other than we had before, meaning that those off-diagonal elements could be non-zero, because my observation of my weight today will be correlated with my observation of my weight tomorrow, and so on and so forth. And if this matrix idea is confusing to you, by the way, think about a correlation matrix. We saw those in the previous course, where if you had variables like x1, x2, and x3, x1, x2, x3, and you have correlations, pairwise correlations between these guys, you'd have a 1, because of course the correlation between any variable and itself is just 1, so we'd have 1s along the diagonal. That's always going to be the case. And then we'd have correlations on the off diagonal. So maybe the correlation between x1 and x2 was like 0.3, and then you'd fill it out with all the correlations between all the variables, maybe 0.5 and 0.5 here. So the idea here was, this is a correlation matrix, just for example. So this matrix is kind of a similar idea. It's describing how these variables relate to one another. Basically, the correlation matrix is just a standardized version of this. And of course, if all of these guys were 0, 0, 0, 0, 0, all on the off diagonal, it would mean all these variables would be independent of one another, right? At least linearly. So that's kind of the idea, going from here to here means those off-diagonal elements are not 0 anymore. And that's really what we need because, if we're measuring the same individual repeatedly, and that's the group, they have to be correlated with one another where they weren't before. So if we want to write this out, noting that if we have m units, and remember we're going to have multiple observations per unit, we can write the data out like this. So for y, like y1 here is going to be the y for the first unit, and you could have multiple measurements with this. And then x1 is going to be the fixed effects for that first unit, and gamma would be the random effect coefficients. Again, in groups, okay? So the thing to remember is each of these guys, so within a group, we're measuring the same thing, which is going to mean that the distribution of those effects will be normal with a mean of 0, just like before. But now, because there's correlation between these guys, the variance is going to be sigma squared d, where this d is going to be some non-diagonal matrix. We write that out, we can then say marginally, so without considering which level of the random effect I'm in, so I'm not considering which individual, just kind of overall, the distribution of the response has the average of x beta and then a variance matrix, which is equal to this. And it's essentially taking the sigma squared along with the lambda we had a moment ago, which is controlling the relationships between the observations within a group. And then we're kind of adding in a function of how all the data varies between the groups as well. Because remember, we have to consider both the within group variation, that's this, and then the between group variation, that's computed from this in a sense. Because what we're talking about here, we're talking about the distribution of y, whereas previously we had y given that gamma, and we consider a particular level of gamma, the random effect. We're not doing that anymore. We're saying just what's the distribution of y by itself without considering which particular level of that random effect I'm in. It's just kind of a different way of looking at it. But the reason it's important to write it out this way is that it kind of implies a few interesting relationships. I want to focus on this guy. So this sigma, now this is the variance matrix, which is going to describe how everything correlates with everything else, all the fixed effects and all the random effects in their relationship with y. This guy is going to be a big block diagonal matrix, which is going to look like sigma 1, which is going to be a matrix for the first level of that random effect only. And then I'm going to have sigma 2 here, and then I'm going to go however many levels of that random effect that I have. And then everywhere else is going to be 0. Every other spot here. Now, basically, kind of what's going on here is that each of these guys, each of these individual capital sigmas within this big matrix, they themselves are a matrix, the elements of which describe the within group covariance. So the within group covariance of a particular level of that random effect, okay? But we already talked about that. We already know that the observations within a group are related to one another. But the important thing here is we note that there are zeros on the off diagonal here. So even though within a group they're correlated, if you go to some other group, it's uncorrelated with the first. Okay, so that's going to be kind of the idea. This is going to allow us to capture relationships when you're kind of measuring the same thing repeatedly. Because you can consider my weight today correlated to my weight tomorrow, but it's probably completely independent of your weight today and the correlation between tomorrow. There are correlation within us as individuals, but between us, there's no relationship. So that's pretty much the background I want to give you on the problem. It's more complicated generally, and if you take a more advanced statistics class, you're going to get much more on this. But I really want to kind of keep it focused on some examples now to see what we can actually do with this. Because really what we need to know is that we have correlation now within groups that's going to allow us to capture things like time dependencies and things like that. So the first data set we're going to talk about is called the Panel Study of Income Dynamics. I don't know whether they call this PSID or PSID, but it's a pretty profound data set. If you want to get access to it directly, you can go to this URL down here. But I believe it's the longest lasting panel data set that's ever been created, assembled on individuals. Basically, they've been tracking these families since 1968. And every year they collect all kinds of demographic information, how much money they make, how many kids they have, and things like that. And in the Fairway package, they've kind of compiled a subset of this data. They've grabbed just the age of the individuals, how much education they have, what's their sex, what year was the measurement taken, and how much money do they make. But there are many more variables in this data set, and actually the data set is pretty massive. And as I mentioned before, you can go to this website here if you want to collect more, but it's been used in many publications. But we're just kind of look at it from a very narrow perspective here, just to, kind of illustrate the idea of these kind of correlated measurements within individuals. So as you might guess, we're going to focus on the income of those individuals over time. That's, the primary varying information that we have here. And the data set, like I said, has a lot of different individuals in it, but we're just going to look at the first 12 right here. And we're going to plot the income for every year and see if we see any trends. So basically, we're going to have a different box for every individual. And just note really quick that the the scale here on the y-axis is on a log scale, just because, income is generally represented on that scale and it just makes things a little bit easier to see. And so what you can notice here is that between individuals, some individuals are stable, some individuals are not stable. Like individual 6 here, you can see when they started being measured here, over time, they made more money. And this is actually a very steady increase. Other folks, on the other hand, not really the case. Person 5, you can see they had a decently rising income and then something happened and they dropped by a lot and then they peaked back up. So this person's income, if you kind of looked at the overall trend here, they're pretty flat. I mean, there's variations up and down, of course, but they're not really increasing over time in any consistent way. And if you look at all of these different plots, you can see every individual has their kind of unique circumstance. And their income trajectories over the years are all very different, and we want to be able to account for that. And so the first thing we could do to kind of illustrate this is, noting that if you were to do like a linear regression just on subject number 6, that has like a little positive relationship here. But if you were to do it on person number 5, they're kind of flat. So separate linear regressions on these would have both separate slopes and y-intercepts. So those two parameters that we have to describe a simple linear regression, they're going to be different between those individuals. So what we can do, if we're using R here, we can actually use in the LME4 package that we've been using when we talk about mixed models, the LMList function will actually fit a linear regression for you by a certain variable. So in this case, we're going to fit the log of income as the y against the year. And we're going to subtract 68 off of this because otherwise you kind of have a worthless intercept. And then we're going to do a vertical bar. And so basically what we're going to say is everything that's after this is going to be our by variable. So what we're going to do is we're going to create this y tilde x, this linear regression here, for every person separately. And so what this will do is it'll take the data set that's given here, it'll split it up by individual, and it'll fit a linear regression within each level of this variable we specified here. Okay, so in this case, we have picked only the first 12 folks in our data set. And what we can see is for each person, for each individual, we have an intercept and a slope. So what we're doing is we're fitting this model right here. We have a y-intercept for every individual, and we have a slope for every individual. And kind of in line with what we were discussing before, person 5, they had that kind of, it was flat for a while and then it dropped down and then it went back up and then it was kind of stationary there, right? That was person 5. And then for person 6, they kind of had a steady increase over time. And you can see that here. They have roughly the same y-intercept. And by the way, all these y-intercepts, they're on log base E scale. In the previous plot, they were log base 10. So in case you were to go back and look at the plots, that's a little bit disconcordant between the y-intercepts, but that's why, log 10 versus log base E. Anyway, their y-intercepts between person 5 and 6, they're roughly the same, but their slopes are different. Person 5, they didn't really have any kind of change at all. Like they were kind of flat, even a little bit negative. But person 6, they had a steadily rising slope. Okay? And across the board, if you compare all of these, they're all a little bit different. The y-intercepts are different, so how much money they were making in 1968, the beginning of the study, and the reason it's interpreted that way is because we're subtracting that off in our x variable. So that's different, how much money they started the study with, and then that rate of increase is also different between every person, because everybody kind of had their own different situation, okay? And so it's important to note that knowing that we have these groups of the individuals, if we were to simply use a random effect, it's not going to work, because all a random effect is going to do is shift the mean up or down based on that person. It's not going to account for the fact that all these different folks, they have different income trajectories with respect to time. So as time is going forward, their changes and their rate of changes is all different between the individuals, and we need to be able to account for that. So let's say we wanted to model the income for individuals, and we are going to use J as an individual index. So it's going to be person J, and then we're going to say at year I. And maybe we think the income for person J at time I is going to be a function of their sex, how much education they have, and what their age was. And this is in the beginning of the study only. So as you go through the years, the age variable is not increasing. It's just how old are they when they first entered the study. Okay, so we've got a sex variable, we got an education variable, and an age variable. These guys are fixed effects. We specifically want to know what is the effect of these variables on that income. So we've got year, sex, we're going to have an interaction, sex by year, education, and their age. Now what we have to do is we have to take into account that every single individual is going to have their own intercept. So this here, this gamma sub j 0, this is going to be the specific y-intercept for person J. So this thing is going to be some random quantity that's going to vary depending on who the person is. And this will shift the mean up or down depending on who we're considering. But that's not all we need. We also need the slope for a year to change, depending on who we're considering. So now we're going to add this extra piece right here. We have another year variable. We had one over here, a fixed effect, but we're also going to have a random effect as well. That's going to vary depending on which person we're considering. So this is going to be a random slope for each person. And I'll be doing another example like this later, but basically if you combine this term and this term here, and then you factor out year, right? Because year is a common term in both of those, you would have beta year plus that gamma sub j, so for that slope for that individual, this quantity times year I. Okay, so now really what we have is we have the variable year, but the slope going with that variable is a fixed slope, beta, that we estimate, a single number, plus some random quantity that's going to change between individuals. And what this is going to allow us to do is have many different possible slopes for all the different people. Okay, and we also note that these guys, because they are tied to the specific individuals, they're going to be correlated with one another. So their joint distribution, so together they will vary. Their average will be 0 together, and they'll have sigma squared d for their variance. So there could be some correlation between the intercept and the slope. Now, to actually build this model in R, there's one little tweak we have to make, because really the only thing that's different is just the addition of this term right here. This is the key addition to your mixed modeling toolkit now has, is the fact that we now have this random slope in the model as well. But if we forget about that for the moment and just put everything in we know so far, we have year, sex, the interaction, and if we want that, we know it's year by sex in the model down here. We have age, we have education, those are also effects here, and that is where our fixed effect stops. So everything up before this line here is all fixed. Now we have our random stuff over here. Now previously what we'd write, we know the grouping here is the person, right? And what we would do before is we would write a 1 and a vertical bar, and then we'd write person over here if we wanted to add this into our model as a random effect. Now what this 1 is representing from all the previous mixed models we've done is it represents a random intercept. It actually captures this part right here. So every mixed model we've done so far is a random intercept model. It just kind of shifts the mean up or down depending on which group you're considering. But all the effects of all the covariates, those are all the same between the different groups. But now, since we have this random slope here, instead of just having a 1 before this vertical bar, we're going to have the year, because we want the slope of this variable to vary between individuals. And by the way, the intercept part is still going to be here. In fact, this term right here, this entire thing in the parentheses, this is actually equivalent to if you were to write 1 plus year FMS. So that variable there, vertical bar person, is the same thing, but you just don't have to write it anymore. Just like we don't have to write it over here. I mean, these models are still going to include an intercept, whether we write out the 1 plus or not. Okay, but that is the key addition here. Now that we have this random slope, because we want the effect of year on the income to change between the different individuals, we want a random slope where that slope is randomly varying between the individuals. And this is how we accomplish that through the R code. Okay, and as is tradition at this point, we run our model, we look at the summary, and we have a lot of information that's pretty similar, kind of to what you've seen so far. There are a few key additions. Now, in our random effects table, where we can look at the standard deviations of all the different random components we've added, we still have our intercept, our standard, kind of person random effect there. But now we have, rather than just the intercept, which is what we had before, now we have this random slope part here. And what I want to call your attention to is this standard deviation right here. So the standard deviation of the random slope part is 0.05 almost. And so what this is telling us here is how much the slopes vary between individuals. And so if we look down here in the fixed effect table, we can see, ignoring the interaction for just a moment, we can see that our fixed effect for the slope is 0.085, okay? So this was equal to beta hat year. Then this number over here, our 0.049, is going to be equal to sigma squared hat year. So the variation, no squared here, is a standard deviation I'm looking at. So just sigma squared year. This is going to be the standard deviation of those slopes. So if we go back to that little analysis that we did before, where we spit out a linear regression for every person, and we look at the slopes for a moment, you can see that if I were to just pick one number for all these guys, I would say 0.85 is kind of a reasonable number, right? Because they're kind of bouncing around, right? 0.84, 0.03. 0.89. You've got some bigger and some smaller than that number, but then they're all varying a little bit around it. and this number is describing how much they're varying. All right, so that's one thing I wanted to call your attention to that's kind of new in this output over here. And everything else is largely the same. We have our response on log scale, so we can, interpret these slopes as percentages. And so we can assume that in this data set, at the beginning of the study, if you were a year older, your income would on average be 1% higher. Every additional year of education gets you a 10% increase in that salary. Another interesting thing we can see here is that we have a significant interaction between year and sex. So what this is kind of saying that is in this data set, because this interaction term is estimated to be negative, it means, since this is the level of the sex variable we're talking about here, it means that when you consider a man, the slope tends to go down. The slope of earnings over time tends to go down a little bit, but because the variable up here for men is high, is positive, it means that men make significantly more than women in this data set, but that their slope is not quite as high. I think it looks something like in the data set, you got the men up here, and then I think the women are kind of like that, I think. There's kind of an interesting takeaway you can take from this data set. Other things we could talk about, we could make confidence intervals for our random effects, just like we've done before. And this is our primary way of determining if a random effect is significant, to do a confidence interval. And we can see, basically if it's away from 0, that means we have quote unquote significance here. So you can see our person effect, both with respect to the intercept and the year, are significant here. So it's kind of worth having those in our model. And interestingly, also the correlation between the intercept and the slope is pretty strongly negative here. And this would mean the higher your income was when you started the study, it means the lower your slope is going to be, which is another kind of interesting thing that would be interesting kind of exploring through diagnostic plots and things like that. And then finally, for this data set, we could do a QQ plot of the residuals, kind of expecting that they should fall on this normal distribution because indeed, we are using a Gaussian distribution as the response here in LMER. But you can see that it kind of has this S shape. And I wanted to include this just because, I always think diagnostics are pretty important to do because it kind of tells you what's going on with your data. And in this particular case, this plot, when a QQ plot has this sort of S shape here, where it goes up and then down, it means your response is heavy-tailed. And the transformation, the log transformation we're doing to this data set is not enough. It's still heavy-tailed. So a different transformation may be in order. Maybe removing some outliers may help or something like that. Okay, so that'll wrap it up for that data set. The next data set I'm going to talk about is this panel data set called the Grunfeld data set. So this data set is pretty popular for economics. And so anybody who's kind of in that field, feel free to chime in and let me know, if there's any other models that folks usually consider in this kind of thing. I'm always looking for new examples, but this data set is a very popular panel data set, and it's comprised of 11 manufacturing firms in the US over about a 20-year period. We can find it in the AER package, which is Grunfeld for the data set, and it has 5 variables. What does the company have in gross investments? What's their overall market value? How much capital do they have? What's the name of the firm? And what year are we considering for that observation? A lot of times folks will call this panel data, and they define that as representing cross sections of data. So like in this case, a firm or a year could be a specific cross-section of data for which correlation exists within that cross-section. But as we kind of just talked about, these panels, they can just be represented by random effects, specifically having random slopes to allow covariates and the response, those relationships to change. So we can kind of capture the fact that we're measuring the same thing over and over again. So with the knowledge we have, let's consider kind of a simple model first. Maybe we want to relate the investments in the firm just to value. All right, so we have the investments for firm I and then measurement J, because for every firm, there are multiple different observations in the form of different years. We could have an intercept and a slope for that according to value. So, you'd think the higher the market value of a firm, the more investments there's going to be. And then we could just have a random intercept for the firm. Keep in mind, when we consider these different firms, remember this guy here is going to change. This is just going to be a normal distribution with mean 0 and variance sigma squared, maybe with an F down here for firm. Okay, so for the different firms, there are going to be different values here for BI, but you have to remember the overall relationship between market value and investments is the same for these different values. All this number is going to do, because it has nothing to do with value, all this is going to do is kind of shift the investment number up and down. But that relationship between value and investments is going to be the same, and that will be controlled by beta 1, whatever that's estimated to be. And so because of this, because we have this kind of shifting up and down, I just want to reiterate the point. This model is called a random intercept model because we have a random effect that has the effect of just kind of shifting that intercept up and down, because this one has no covariates. So when we have a random value in here, it's just going to combine with the beta 0 to just give you a new intercept. specifically one that is random, hence random intercept model. So we want to fit this model here to our data. And the reason we want to do this is because we can look here very quickly and see that every single different firm, which are represented by these panels here in this grid, every single one of them, they're in a completely different area, right? Like General Motors has very high levels of investments. American Steel is much lower. So you can see at the very least, each of these points, whether there's a strong relationship or a weak one, each of these sets of points, they're definitely in different places with respect to their investments, right? They're shifting up and down. You can also note that the relationships between value and investments is different between them. We're not accounting for that right now, right? We just have our random intercept in the model I showed you on the previous slide. So like IBM looks like this. Atlantic Refining doesn't have quite as strong of a relationship between value and investments. You can see that slope is not quite as strong. And we'll see, kind of what this implies with the model we've selected in a moment. So what we'll do to fit this model is kind of what we've been doing already. All we're going to do is we're going to say, I want to look at the investments as a function of value, and then I'm going to have a random intercept according to the firm. What we end up getting out of this is a coefficient estimate for the relationship between value and investment that is positive, significantly so, which is kind of what we expect, because when we look at these, even though not all of them have quite, a very strong relationship between value and investments, generally speaking, as we would expect, there is a positive relationship between them. So we end up with a positive fixed effect estimate for that coefficient. But that slope is going to be the same for every firm. And then, of course, we have our firm random effect, which is going to be a random intercept. So we can see this is how much these firms are varying between them. And you can see this number is very large compared to the fixed effects estimates down here. So, as we would kind of expect, there's a huge variation in the amount of investments for the firm. So it's very good that we're trying to, capture that variation there. But if we plot the data, where we're looking at this a little bit differently compared to how we looked at it before, previously we had a separate box for every firm, but just to kind of drive home the point of what we're doing, now we have different colors on one plot, and these different colors represent our different firms that are in the data set here. And these black lines here represent, within each firm, what do we predict the investments to be out of that model that we just built using just a random intercept. So we have the value on the x-axis, the investments on the y, we have our different firms and kind of where they're falling. And so now we can see what I was kind of mentioning before, is that some of them, such as these green points that are kind of tucked away here, there's a reasonably strong correlation between those. As the value is increasing, so are the investments. For some, it's a bit weaker though. If you kind of forget about the line that's here, you can see these kind of dark yellowish points here. There's actually not that big of a relationship here. If you were to draw the line here, it'd be pretty flat. But because we only have one number for the slope relating value to investments, we're not able to capture that relationship. That difference in the relationship between value and investments is not able to be captured with the model that we fit on the previous slide, because we only have one value for the slope. But you can see how straight of lines I can draw here. You can see that each of these lines, if I were to kind of trace this back down to here, here's the y-intercept. If I trace this line back to the y-intercept, sorry, the intercept would be here. If I trace this line back, you can see here's the y-intercept. You can take each of these lines, which are completely parallel, and note that they all have different y-intercepts. That's why we call it a random intercept model, because that BI that we had in the model is just going to shift you up or down with respect to where it intersects the y-axis. And this is not what we want for a panel data set, right? Because we have time trends and we want to be able to kind of account for that. So now what we're going to do instead, realize that what we really want to do is we want to capture the individual slopes and intercepts within each firm. Previously, we had our beta 0, our beta 1 times value, our random intercept. Now we're going to add a new term. Now we have B1I, which is going to be the random slope for value. And just like we had before, these two guys are going to be correlated with one another. Okay, so now, if you kind of rearrange all the terms here, you can sort of see how it works. If we take the things that do not have value, so if we move this guy over here with the fixed intercept, we can see our intercept for this model is beta 0 plus B0I, where this guy is a fixed number and this is a random number. So we have a random intercept. Now over here for the slope for value, combining these two guys together and then factoring out value, we can see we've got beta 1, which is a fixed number, and then B1, which is a random number. So we have a random slope as well. And so the random intercept and the random slope, these are going to allow both the intercept and the slope to change depending on which firm we are considering. Okay, and just like before, we're going to fit this model tucked right up here. Almost the same formula we had before. We have the investments and our Y, our value here, but now rather than having one bar firm, we are going to have value bar firm to say we want a random slope between the different firms. And now you can see all the different lines, they all have different slopes. It's not just one slope and they intersect the y-axis at different points. They have different intercepts still, but they also have different slopes. And this one much better captures the relationships within firm and their specific relationships between value and investment. So anytime you think you may have a data set where this is true, where you've got a group and you have a covariate as well, and you think that relationship between the covariate and the response may be different depending on which of those groupings you're considering, this is how you do it with a random slope. Okay, another model we could fit, now we can kind of bring the year in as well. And so a much bigger model would say, I want to consider both the market value and the capital held by the company to see if that determines how much investment they have. But then I also think both value and capital may be different by year now. So if these guys are different by year, that means we're going to have different slopes and intercepts for the both value and capital by year. So if we fit this model and then generate a similar plot we had before, we can see this captures pretty well what's going on with the data. Some things like General Motors, I mean, this is sort of overfit almost. I see this model fit in a lot of the, examples of the Grunfeld data set, and I'd never seen an actual plot like this before though. And so you can see that the predicted values given by this line are tracking very closely with General Motors, but not really with some of these others. Like in the middle here, the orange line is not really tracking very closely to the orange points. And same with kind of the dark yellow one. But nonetheless, this is the fit that I typically see when I look at examples with this data set. But what this model will allow us to do, kind of disregarding the fit for a moment, is it will allow us to have different trends for value and capital with respect to the investments by year, instead of just by firm. And looking at the output of that model, we can see that the fixed effect estimate is actually not that much different for value. Previously, you could go back and check if you'd like, but the estimate for the slope for value was roughly around 0.16. So we haven't strayed from that all that much. But with these random effects that we have, we can see that depending on which year we're talking about, this slope could vary according to this standard deviation. So this would be telling us within a particular year, how do these relationships between value and investments vary? Between the firms now. We're not within firms anymore, we're between firms, but within a year. So even though this fixed effect estimate is not that much different from before, because remember, at the end of the day, we're still talking about the relationship between value and investment, but we can try to capture variability across different things. So in this particular case, we're fixing the year and we're saying, if we consider a year, what's that variability look like between the firms? That relationship between value and investments, how much does it change? That's given by this number. And then same thing here with capital. And so really, at the end of the day, I mean, this is what panel data is. There's a pretty big body of, ways to kind of analyze these data sets. Like most of the stuff I was able to find in R was this PLM package I found. But most of the panel analysis that you could do can just be implemented as a mixed model. Now that we have this knowledge about, what it's actually doing, we're measuring the same thing repeatedly, and therefore that is like a grouping variable. And then we can account for different relationships between covariate and response with those random slopes that we've talked about. But if you use the LME4 package instead of some other package, it gives you a lot of different options. Like basically the entire suite of things that we've done with mixed models, all of your, model comparison techniques, your confidence intervals for your random effects, and so on and so forth. You have a lot of different tools at your disposal if you just fit the models directly with the knowledge that you now have. Because really, this entire thing with the random slopes, it's just trying to capture the correlation we have within groups. Observations on the same person, on the same firm, or whatever. And these random slopes really, they allow you to capture some pretty complicated relationships between groups. It's essentially like a kind of a souped up interaction model when you have a random variable that you need to account for. Okay, other things I want to mention, the same diagnostic test that you have access to, all of your, residual plots and things like that, all of that still applies to this. You do all the same diagnostic checks because, again, it's just a mixed model. You can do the same stuff you've done before. And then finally, I want to mention that, I didn't write it out here, but if you have a non-normal response, you can do the exact same thing by using GLMER and just picking your response distribution. Same idea. So pretty interesting idea. The way we're able to capture this is just by a simple addition of that random slope. But now that we've kind of gone through this is the end of mixed models in the course. It does, compose most of the course itself, but from here on out, we're going to kind of study a few interesting and different topics. So that'll be it for this one. Thank you.